Hello and welcome to the presentation of the paper entitled Multi-Partner Project Multi-GPU Performance Portability Analysis for CFD Simulations at Scale. This paper is scheduled to be presented in the Design Automation and Testing Europe Conference on 20 to 22 April 2026 in Verona, Italy. My name is Panagiotis-Eleftherios Eleftherakis and I am with the National Technical University of Athens. This work has been developed in the context of EU Horizon 2022 Project RefMap in collaboration with KTH Royal Institute of Technology, Hewlett-Packard Enterprise, the Technical University of Delft, and the University of Michigan. In this presentation, we will provide a brief introduction of the RefMap project and an overview of its general workflow. Having presented the motivation for the portability analysis that takes place at scale for the high-fidelity CFD simulator SOD2D, we will provide an overview of the numerical model of the computational fluid dynamics simulator, as well as its software implementation and hotspot analysis across different configurations of its solver. Then, we will specify in detail the multi-level parameter space across which we explore its performance and aim to improve its dataset generation throughput with targeted memory optimizations. We will then move on to the evaluation of the proposed optimizations and the insights gained through the portability analysis. We will conclude the presentation by summarizing the main achievements of this work. RefMap stands for Reducing Environmental Footprint through Multi-Scale Aviation Planning. It is an innovative project focused on creating sustainable aviation solutions, aiming to improve air traffic management at both microscales and macroscales, referring to urban air mobility and traditional aviation respectively. We aim to reduce environmental impact of air travel and minimize noise impact on communities and wildlife. An integration of the related tools is provided in the RefMap online platform. Within the scope of RefMap, this platform serves as a digital service developed to quantify and minimize the environmental footprint of air mobility for both UAM and large-scale traffic flows. By processing environmental data, such as wind, noise, and emissions, the project provides the analytics required for evidence-based policy making and the creation of sustainable aviation business models. We will now provide a brief demonstration of the RefMap dashboard. As mentioned, it comprises both large-scale as well as small-scale tools, each of which comes with the appropriate documentation. We can configure the tools by selecting the appropriate parameters for each of the filters present. Thus, we can obtain simulation results across all the selected parameters. We will now move on to the general workflow of RefMap. RefMap targets low-latency, multi-fidelity urban airflow prediction to support sustainable, innovative air mobility. As seen in the figure, the low-fidelity branch is driven by the OpenFOAM CFD simulator and accelerated by the NVIDIA AMGX solver, executing a model that aims to evaluate the neighborhood scale wind-associated risk. Regarding the high-fidelity framework, the SOD2D simulator is employed and analyzed in the rest of this paper. With the simulator, high-resolution direct numerical simulations generate turbulence-resolving data to train compact, fully convolutional network models for wall-based flow prediction that undergo extensive optimizations such as structure pruning, compression, and compiler-level optimizations, achieving up to 50 times compression with negligible loss in accuracy, thus significantly improving latency and throughput. They are deployed at the edge or in the cloud, enabling UAV trajectory optimization and high-fidelity sensor placement. On CPU-only systems, such cases require weeks or even months to compute, limiting the datasets for surrogate training. RefMap overcomes this bottleneck by extensive auto-tuning and performance exploration of SOD2D. Moving towards RefMap's mature phase, multiple infrastructures were employed, necessitating multi-level performance exploration, spanning across hardware, software, and application-specific parameters. The rest of this paper will focus on the performance portability analysis that enables efficient generation of datasets for surrogate model training within the RefMap workflow. The SOD2D simulator utilizes the spectral element method, a variant of the finite element method, for high-order accuracy on unstructured meshes to solve compressible Navier-Stokes equations seen in conservative form on the right. The colorized terms highlight temporal evolution, convection, and diffusion that are going to be highly relevant in the rest of the presentation. Temporal integration utilizes a fourth-order Runge-Kutta scheme, and the simulator is GPU-enabled by OpenACC with MPI for multi-node scalability. This figure illustrates the execution flow of SOD2D's various computational kernels, represented by the blue rectangles. The algorithm is structured around the loop over 4 Runge-Kutta steps as described previously. Within each step, the necessary values for evaluating the Runge-Kutta function are computed, and this is followed by the evaluation of the diffusive and convective term residuals at each point n within every mesh element E. The focus of this work lies on the computation of the diffusive and convective terms, highlighted by the red arrows, a process divided into three subparts: preloading, execution, and storeback. These subparts are executed independently with synchronization barriers indicated by dashed lines. Each term computation iterates over all elements in the mesh, and the element loop is distributed across fully parallel gangs and vectors within gangs, each with sizes defined by the kernel's execution parameters. We will now provide the hotspot analysis for the simulator run on representative platforms within the context of RefMap. In the uppermost right figure, we can see Taylor Green Vortex runs on the NVIDIA AN100 equipped Berzelius cluster, where it appears that the convection and diffusion kernels emerge as the primary hotspots and dominate at scale. Auxiliary functions can be removed once simulation correctness is established. Subsequent analysis focus on the channel flow case as well as more representative to airflow in urban environments. At bigger scales and across a parameter space seen on the right, performance profiling reveals consistent hotspot behavior across both simulated cases, with the convection kernel dominating execution, amounting for up to 50% on NVIDIA and 70% on AMD, followed by the diffusion kernel at 22% and 10% respectively. The convection kernel remains the primary computational bottleneck, showing notable sensitivity to floating point precision and GPU vendor and mesh size. This is exacerbated on the MI250X due to register spilling. The emerging hotspot analysis applies throughout the space, and the rest of this work targets the aforementioned kernels. Thus, we define a multi-level parameter space for the performance exploration and tailored per scenario optimization of the SOD2D simulator. The parameter space spans application input configuration regarding the case selected, solver type and mesh size, runtime parameters regarding floating point precision, memory access optimization targeting cache behavior, memory coalescing and register usage, software infrastructure parameters regarding compiler stacks and the programming framework, and finally hardware infrastructure parameters regarding the cluster, GPU type and number of GPUs. The best performing optimizations are determined per point of the parameter space. We will now analyze in detail the memory optimizations utilized. In total, they comprise the modification or addition of 6,200 lines of code. The kernel splitting optimization is motivated by the fact that on the AMD MI250X, in the default SOD2D kernel design, computation of all gradients happens within one kernel, which leads to high register usage per thread. To reduce this pressure and simplify kernel behavior, the original kernel was reorganized into three separate kernels, each responsible for one equation system corresponding to mass, momentum, and energy, respectively. The pseudocode structure of the split approach is shown in the rightmost figure, where each variant operates independently and carries only the data structure it needs, increasing kernel launch overheads but leading to much lower register usage. As mentioned previously, preloading is utilized in the baseline SOD2D implementation, intending to improve spatial locality by removing indirect addressing and improving access regularity. This is achieved, as seen in the left, by preloading global structures into per-element local arrays, bringing it closer to computation and going through the same loop bounds as the computation. It has been observed, however, that for most architectures and inputs, this overhead is not necessary, and accessing global gradients directly with index linearization, as seen on the right, provides significant speedups. Preloading, however, is highly effective when paired with prefetching. Prefetching is implemented through the OpenACC ACC cast directive, and according to the standard, this directive is tied to a loop structure and informs the compiler that the specified subarray should be brought into the highest cache level for that loop. If we were to apply it to large global arrays as seen in the previous slide, it would provide little benefit, and for this reason, we apply it to element local arrays created by preloading. Prefetching every quantity in every nested loop is also ineffective, so the directive is only used for the quantities involved in the deepest nested computations within the quadrature evaluation. We have performed a thorough exploration of these quantities and came up with the structure seen in this slide. As already mentioned, in the direct access variant of SOD2D, memory coalescing is hindered by irregular access patterns, especially in quadrature statements where the connectivity matrix combines with index linearization, as seen in the deepest nested line here. Since the connectivity and index linearization matrix depend only on the static mesh topology, their mapping does not change across kernel launches. In order to avoid recomputing the linearization and indirect addressing, the combined result of these matrices is stored during the first launch into a compact lookup matrix indexed by element node, quadrature index, and polynomial order. All subsequent launches then access this lookup table directly with regular and coalesced addressing as seen in the line here in computation. For this approach to remain efficient, the lookup matrices must remain sufficiently small to fit within the lower levels of the memory hierarchy, and for the architecture seen within the context of this paper, no improvement has been observed. We will now move on to the evaluation section of this presentation. For every point within the multi-level parameter space, we have collected the average SOD2D times the runtime. Each box within these figures corresponds to the average runtime across 5 runs when scaling the input geometrically from 1 million to 16 million mesh nodes. Only the channel flow case is presented here due to high similarity of the results between cases and due to the fact that it is more representative of real-world applications. For a given combination of floating point precision and GPU architecture, the box annotation signifies speedup with respect to the unified baseline kernel configuration. Regarding the comparison between NVIDIA and AMD GPUs, significant slowdowns are incurred when transitioning from the A100 to MI250X, namely 23.38 times on single precision and 8 million mesh nodes. This is attributed to suboptimal power caps on Lumi GPUs, namely 20% less than their nominal value, the use of a single GCD on the MI250X, the Cray compiler stack for OpenACC on AMD being less optimized for the underlying hardware than the respective NVIDIA compilers, superior performance of the NVIDIA GPUs on single precision, and register spilling on the MI250X as previously mentioned. We have found that the optimal combination of configurations to reduce this performance gap is kernel splitting paired with preloading and prefetching. The impact of kernel splitting is highly variable across vendors and floating point precisions, but mostly consistent across cases. For single precision, it speeds up the execution on AMD, but incurs a slowdown for NVIDIA. Interestingly, as seen in the figure, the opposite behavior is displayed for double precision. Preloading paired with prefetching consistently improves the baseline performance. The effect is mostly minor, except for AMD MI250X on single precision and NVIDIA V100 on double precision regarding the split kernel. In the former case, a 42% and 60% speedup is provided for unified kernel and split kernel respectively, when in the latter, the respective numbers are 63% and 25%. In these figures, the no preloading variant corresponds to the direct global access optimization shown before. We note that the baseline SOD2D comes optimized with the expensive preloading technique. Since inherent prefetching to caches in the no preloading version can be equally efficient, it is not obvious whether the benefit of preloading compensates for the overhead of the preloading block. As seen in the figures, the no preloading version always outperforms the baseline, with the exception of the split version with double precision on the MI250X. This effect is greater for double precision than single and more prominent for the AMD MI250X compared to NVIDIA GPUs for single, while the opposite is true for double precision. We also note that the regular access optimization underperforms on the architectures explored due to the size of the regular matrix being 18 times that of the irregular one, exceeding the capacity of the lowest parts of the memory hierarchy. In the context of the scalability analysis of SOD2D, we evaluate the efficiency as a metric of throughput. Thus, we introduce the giganode operations per second metric, which is the total mesh nodes times Rank-Yakuta steps times total time steps divided by SOD2D average time step runtime. The giganode operations metric emerges from the homogeneous way the nodes are updated. Thus, we perform 160 weak scaling runs, scaling the input proportionally to the number of GPUs, with about 1 million mesh nodes corresponding per GPU. As shown in the rightmost upper figure that shows channel flow scaling for single precision, scaling is mostly consistent for all of the optimizations. However, we observe that channel flow demonstrates high inconsistency between scaling of different memory optimizations, with optimal configurations alternating between different scales. Both sublinear and superlinear speedups are observed, depending on mesh partitioning. Regarding the comparison between single and double precision, single precision displays 1.2 higher giganode operations per second than double. We report that the split kernel with preloading and prefetching is the optimal across scales except for 32 GPUs. We attribute this to the redundant preloading operations at this degree of partitioning. For channel flow, the improvements from worst to optimal configurations at maximum scale are 23.8 for single precision and 14.6 for double. Therefore, as is apparent in the figure, selecting an optimization for channel flow at 64 GPUs based on the optimum of 32 would incur a 23.8% penalty for single precision and 8.3% penalty for double. The above analysis provides the key insight that low-scale optimization choices don't reliably extrapolate to larger scales, and accurate modeling is needed at scale. Concluding this presentation, we provided a multi-level performance analysis for high-fidelity CFD simulator SOD2D in the scope of the RefMap project, spanning across hardware and software infrastructure parameters, application input configuration and runtime parameters, and thus constructed tailored memory access optimizations for the hotspot kernels of SOD2D and evaluated them across the multi-level parameter space. Notably, we observed 0.7 to 3.9 deviations in acceleration speedup across the space. We narrowed the cross-vendor performance gap by up to 2.7 times through the memory optimizations. We identified the best performing memory access optimizations at scale across the space. And we provided the insight that scale-aware memory access optimization could yield 23.8% speedup with respect to mere extrapolation. Thank you very much for your attention.